So I really can't sugarcoat the word problems in 8.4. These are seriously difficult. And if you go on in math, you're not going to find harder word problems than what you see in 8.4 and any other Pima math course. This is really the high water mark. These are seriously difficult. Now, this one involves two airplanes. And so I started to sort of create a picture. I always have a halfway spot in nearly every word problem. And so I created plane A and plane B, and I showed that they were traveling. And I wasn't sure if I was going to make marks on this in terms of their distances traveled or whatnot. But as I read on, it really became apparent to me in terms of where I needed to go next, because we had distances and we had rates here, that is speed, and we had time. And immediately that clicked this famous formula. And that's the way it should always be. Whenever you have those three quantities, you're thinking in terms of distance equals rate times time. And so the classic way to solve that is to set up a table and fill in the table with the information for plane A and plane B. Now, I suggest if you can see it, I know I can't get the video to be large enough, but if you could see it, you'd stop right now and see if you could generate these three color-coded columns with their colors from up above. So what I'm going to do is just read that. In fact, plane A, they tell us very little about it. All they tell us is that it goes 6,300 kilometers at a certain speed. So I know it's going to go that far. And I don't know the speed it goes at, so I left that as a variable. And I don't know the time it's in the air. And so that's the best I can do in terms of uh, this particular distance equals rate times time. Now plane B, it goes this far. And so there is that 4,500. And then the speed is given in terms of plane A. It's 50 kilometers per hour faster than plane A. So this is how fast plane A goes. And so I said, well, we go 50 kilometers per hour faster. And I write this speed in terms of this one. So I do not introduce a new variable. That would be a critical mistake. The fewer variables, the better. And it's the same thing with time. I don't know how long in the air plane A is. I don't know how long in the air plane B is, but I do know not only does it go faster, it's in the air for 3 hours less. And so that's why I took the time for plane A and subtracted 3. Now, they're asking us here for the speed of the two planes. And, I've worked enough of these to pretty much know where to go next. And so I know I want to solve this for R and this for R. And since the rate has to be the same for both of them, I could create an equation and solve it using chapter 8 techniques. And I'm going to do that for you. But, the chances of you maybe seeing that equation and generating it aren't too good. I mean, it's very tricky. And so I've been emphasizing this idea of playing with numbers all semester long. And that's what I want to do. I'm assuming you could get this far and that you wouldn't know where to go next. And so what I suggest we do is we play with some possible times and to see if that unlocks our brain and allows us to set this equation up. So let me go to my Google spreadsheet and show you some interesting things. So if you watch my number play, my number experiments over there on the spreadsheet, you know that I actually stumbled on the answer and a technique for solving this. The idea was to think of this as a system of equations. I have two equations in two unknowns, r and t. The difference between this and chapter 3, where we'd use elimination or substitution, is in chapter 3 we had linear equations. In other words, we had r plus t or r minus t, and it would graph as a line. Here we have a multiplication between the r and the t, and this will graph as something much more complicated than a line. And so the techniques don't straight translate, but the overarching idea does. That is that we have a system of equations, and here I've ripped them out to show them as a system of equations in two unknowns. And we want to know where the intersection of r and t of these two equations are, and it will be an ordered pair, r comma t. So I wanted to know if Wolfram Alpha could solve this just as it is right here. And so I typed that in and asked it to solve it. And as you can see, I put a comma between the two equations, just like we did in chapter 3, and said solve these two, and sure enough it came up with two answers. One in which time is negative, and that does not make sense, and one in which time is equal to 9 hours. And that forces the R to be 700 kilometers per hour, and that's the same answer that we found over in the spreadsheet. So the question is, how do we do this in terms of chapter 8 though? And so, like I said, two equations and two unknowns. I'm thinking to use um, substitution here. And so what I did was I actually solved this first equation for R by dividing both sides by t to get this. And then I solved this equation for R. I didn't do these multiplications. That would lead to trouble. Instead, what I did was I divided both sides by the quantity t minus 3. And that was nice because what happens on the right-hand side, obviously, is these cancel. And then to solve for R, all I need to do is subtract 50 from both sides. So that explains this construct over here of R is equal to this. That's for the second equation, and R is equal to this for the first equation. Now, if R is equal to this and R is equal to this, and it's the same R because it's a substitution, well then obviously I can replace one R with the other R, and this has got to equal that. And that is in fact what we do. Let me show you that. Here is R solved for the first equation. Here is R solved for the second equation, and they are equal. And now we are really in chapter 6. We have a rational equation. And so the game here was to clear fractions. And I multiplied both sides by the least common denominator, t times t minus 3. When I did that, I ended up with this equation. The fractions, of course, collapsed. That was the game. My next step was to do this multiplication and this multiplication to combine like terms and to get everything on one side and 0 on the other side. And that left me with this. I then saw that everything here could be divided by 5. And so I divided both sides of the equation by 5. Of course, 0 divided by 5 is just 0. But 5 goes into this 378 times. 5 goes into 165 3 times. And of course, 5 goes into 5 once. So that left me with a trinomial that was easier to crack, or you could run the quadratic theorem on it. I went ahead and tried to crack it, and lo and behold, two numbers that multiply to negative 378 and add to 33 are plus 42 and a negative 9. And the values of t that make these entities 0, well, t is equal to negative 42 and t is equal to 9. Of course, we know that's an erroneous solution, and we know that 9 hours is the solution for t. And so we still have to find the rates. That's what this original problem asked us to do. We now know that t is equal to 9, and so it's a simple substitution here, and we get 9r is equal to 6,300, and we can divide both sides by 9, and that will bring us right up to the door of the answer. When you do this division, you of course get 700. So R is equal to 700. That is the rate of plane A, and R is equal to 700, so the rate of plane B is 750. So 700 will go here, 750 will go here, and basically we're done. Extraordinarily difficult problem. Like I said, these are top of the food chain in terms of PIMA, all of the PIMA math class word problems. You won't find anything more difficult than this. And so all we need to do is put those values in here. Plane A travels at 700 kilometers per hour. Plane B travels 50 kilometers per hour faster than plane A, so it's going to be 750 kilometers per hour. And let us do a submit. And as you can see, we've got them both correct. Very difficult problem. I hope that helps.